Hi, my name is Peter Hill and I'm researching away at the best way to give tutorials on exams, and this current exam is the 2017 High School Certificate Examination for Australia in the state of New South Wales. It's the physics exam, and I'll give a bit of an introduction about myself first off. You'll see me going through here. About myself, I'm Peter Hill. I'm a teacher. I'm also a quantum physicist, and I'm just going to play around here. Now, this here is the Schrodinger wave equation. It's the basics of quantum physics. So at school, you'll learn this type of stuff. You should be familiar with F equals ma and that type of stuff. Now, these equations were really overturned way back in 1926. So if you study more as a scientist, you'll come across using the slightly more complex equations here. It's particularly this equation down here is one which is very familiar with, which describes wave functions and beautiful shapes and objects and all the beautiful physics that you see. And so unfortunately a lot of the content in school is locked up in this older physics, which is indeed wrong in many more key aspects, and it's rather a balancing act to get through it. Now, just about my background. As a molecular physicist or quantum physics physicist, I discovered a fairly wide range of very small molecules, and as you see up here, the molecules have a different shape. So inside you've got the small molecule, and outside you have the different shape of molecules as imagined or understood now by modern computers, modern scientists. I use my understanding of quantum physics to help me build and understand, unpack high-powered lasers, and in general I really like spectra, which you can see a few spectra here. You'll see those obviously through spectroscopes, little diffraction gratings, but for me they're sort of like the music of physics, the music of atoms. I really get into that. Stop for a moment. Now, I use this practical experience in various aspects of science. Now, the first thing I suppose I did was use lasers to build optical fibre devices, and one of the things is that the knowledge of quantum mechanics is absolutely critical here. I'm just here changing this. Now, this is your typical textbook diagram of an optical fibre, and this is the physics of this is all incorrect. You actually have to, a optical fibre that is the build our civilization is built with is actually a quantum mechanical device that actually produces I suppose a Gaussian wave front out of it. It's all quantum mechanical fields inside optical fibres. So in general, this stuff, which is taught in schools and in textbooks, is incorrect. But it's absolutely necessary to do optical fibre physics and build optical fibre lasers, etc. I was involved in industry in hotel building that. I also, after this, used robots, very similar. I actually used 3 of these robots here, these ABB 2400s, and built a robot factory and used high-powered maths to actually get the robots to cooperate and talk to each other. And I've subsequently continued to build on the use of fairly advanced maths and combine it with automation. And so here you have down here the Automator software. It's a suite of software which I've built to develop things, and I've also developed over here a set of conversion podcasts into mobile phone apps. But as I go ahead, I realise that I have to actually explain things in a little more detail with some visual aids, which is unavailable with the podcasts. and generally build on by training and understanding. I have one more slide on this one. Another dimension to all of this is the many years I spent involved in different aspects of training, army training and stuff like that, and the understanding that a lot of performance is based on getting the actual correct techniques, correct understanding in the correct way to the correct people in the correct method. And so there's a general understanding that you've just got to keep on improving and keep on working away at things, and this is an example of me just getting out there and trying to improve. This is the first multiple choice question of the exam. Well, I'm just going to read it through first. I'll take a little bit of time on this and then I'll talk a little bit about the style and stuff like that. So the first question is, who was the main advocate for the distribution of DC electricity to cities? Now, I'm going to spend a little bit of time going through the actual individual points, teaching points here, but let's talk a little bit about the actual style here. So ahead of the actual multiple choice question, you will typically get a simple unconvoluted who, what, which, where. You may get some leading information, then after the leading information they'll give you the question. Now also in here you'll note that the alternatives are given in alphabetical order. So in this case they're given in alphabetical order. If it's like that, if it's numerical it may be increasing. So there's from small to large, they won't be out of order. Or if they're different answers, they'll be arranged in terms of rank from the shortest answer to the longest length answer. Of course, it doesn't go here. Also note here that they have a point here, so you can't read that as Edison. That's really the only reason. Again, here they could, in some things, they put a little curve there, and that's decided to be visually more complicated to understand. Now, the answer to this is that Edison was the main advocate of the distribution of DC electricity to cities. But I'm going to just take it a little bit more slowly and start to work backwards, sort of reverse order, synthetic answer. It's actually perhaps good when actually describing, explaining things. So we all understand that's what cities are. Cities are a group of customers in close proximity. And now let's stop for a little while and look at DC electricity distribution advocate, and then we'll go through Edison, Faraday, Tesla, and Westinghouse. So here we're doing this reverse synthetic answer, looking at this question and looking at DC electricity and the distribution of it. So you'll see around here a typical DC cell. Let's get it up for you, mate. Okay, and get the colours I like. Sure. So here's your DC cell here. And what's important is that you've got this positive electrode where the mythical positive charges come out, but it really means that electrons come out this end. And you've got a zinc, typically a zinc casing, a some sort of ammonia iron paste in the inside, a carbon core in the centre, and the positive charges, or the classical charges, come up through here. Now the actual reaction is that the zinc is more reactive than the hydrogen ions in it. So the zinc migrates into the paste, and the hydrogen ions combine and form hydrogen gas. So you get hydrogen gas, H2. I'll just write that here if I can. H2 gas is emitted from it, and so the mass of the battery doesn't change very much, but the actual mass distribution changes. There's less on the casing and it goes towards the, you get hydrogen gas coming off. So the electrons go along, jump onto a hydrogen ion, so the electrons get locked away here, and they actually emerge. They go through the light bulbs, and the actual electrons then float into the room on hydrogen molecules. Now, this is something that it's actually rather painful to hear people who really don't understand how it works describe it. And the electrons are produced by the battery, and they go around, and somehow they're stored, or they're actually not really stored back in the battery. This is in a disposable C-cell, or whatever it is, battery like this. Is your familiar batteries. The hydrogen gas comes off it. So people really don't really follow what's happening in a reaction. Now, by convention, we have positive at the top and negative at the bottom. Positive at the top, negative at the bottom. So you can convert this into a P, and that into, it's hard to draw it here, that into an N. So you can see positive and positive at the top. But a good fraction of books have the negative of the top because it looks more stable, but you always in general have the positive up here. And this is not really a distribution. This is the distribution of electricity within a household, and you tend to have things in parallel like this. The electrons will come out here. I don't know whether you can see this. They come out here, go along here, and go through different routes down through the light bulb. You get light coming out here. Electrons will travel along and eventually come out the top here with hydrogen gas. Now, in general, this is not taught at school. Now, I have this, so if you're going to distribute it, you'd have wires connecting different circuits, and different customers would switch on the circuit. I have here the school book picture of a resistor. Now, I think in America you're still allowed to have that as a resistor, but in Australia we have here the actual definition of resistor. So this is a variable resistor here. Variable resistor, 5K variable resistor. Transistor. And I have to really remember about the emitter collector base. Base here, I have to re-see that. This is part of it. Another resistor here, a Zener diode here. So this is a diode with a voltage breakdown. And it goes up to a certain, it's a resistor up to a certain point, then it stops. And this is a light emitting diode down here, all these circuits around here. But the important thing here is these are resistors, these are loads, these give out energy, and that's the proper Aussie symbol that you have here. It's really complicated because people are dedicated to this style of symbol over here, the little zigzag. That's out of date, and it's no longer, I suppose, legal in Australia to call it. So it gives you what DC electricity is. And I've got a little bit of a symbol here to show you the difference between DC and AC. This is an AC generator, a classic AC generator. And as this wire sweeps up through the field here, so you notice the field travels from the north to the south pole. Now, this is a thing that people often get wrong in books. They draw it as an arrow. Now, of course, the magnetic field fluxes, the way that you draw it is the line across here, and this, it never stops. That's the way to draw it here. This is an incorrect drawing, this one. I've just taken it off the internet. Also down here you can see as this wire sweeps up and down, the voltage gets pushed across. So as the wire is travelling, the wire is actually travelling through the magnetic field, and that's effectively a current. The wire, a little wire's current of positive and negative charges, and they move across. And I should mention that electricity travels well in, or electrons travel well in metals. They don't travel well through liquids. They have to actually convert to an ion. So this is how a battery crosses. It's actually an electron valve. That is, electrons cannot travel directly to your hydrogen up here, the electrode here. So the electrons have to take a long route around your circuit and travel all the way up here, because they can't get through here because there are ions in here. So this is a AC generator, and we can convert AC to DC with this section here. This is a split ring or split part commutator with the brushes on the outside, so it actually switches either side. So we'll get on to more discussion of this in a very short while. I'll come back for a little bit at the end of this just to quickly review transistors, which just left my mind for a moment. I came across it. So although Edison was a United States inventor, I suppose, but chiefly a businessman, entrepreneur, and so he used tactics which we would typically associate with shonky businessmen now. So there's a picture of him holding his light bulb, and he basically almost faked the invention of the light bulb. Or he actually didn't invent it, he bought the patent from a French person who actually did invent it. But he could only get it lasting a few minutes, so he actually got the people he was showing it off to actually go one by one, and he would put in a light bulb. He'd show for a while, then he'd take it out and put another one in, and get the next person to come through. Now his main thing was that he had backed the DC generation, DC distribution, on the basis that it was the only safe thing. You couldn't electrocute yourself or necessarily die from a DC voltage. You required the AC voltage to fight or disrupt the heart. So AC is far more lethal, and so he used to go around New York providing service of killing dogs with public executions, and he also had this public execution of an unusually large African elephant that was in Coney Island. They had a herd, the United States had a herd of elephants, and they had an unusually large bull elephant, so significantly larger than most elephants apparently, and it had been abused by its owners or its trainers, getting it to drink whiskey and smoke. It had killed several of its trainers, and of course the United States District Court tried this elephant and sentenced it to death. Edison they obliged by having public electrocution with AC electricity to prove that AC was like that. The actual physics of it is that customers are not so much interested in the current or the voltage, they're interested in the amount of power, the amount of watts, the amount of heat or amount of work you can get out of it. So that equals P equals IV. Now, there's another equation, and I've got it here. Unfortunately, I should do here. Get this colour right. Sorry. Now look, I have to really apologise for this because part of the thing is I have to actually produce these really quickly. But the loss in the power line is proportional to I, or it's proportional to the I times the voltage, and the voltage is I times R. So the R is the resistance of the interconnecting wires. So if you put here the resistance of the interconnecting wires, and I is the current going through it, this is your loss. So DC necessarily had no way of manipulating the voltage. And of course, with intermediate transformers, you can actually step up, step down the voltage, and this is that you use your AC to drive an electromagnet, which therefore drives a larger magnet, a larger magnet with more coils in it, and the amount of volts per coil is constant. So you can go from low voltage to high voltage. Therefore, by increasing this, the voltage, and reducing this one here, you can actually reduce your loss by reducing this value here. stop this. Now, the second option in your question was Faraday, and he wasn't an advocate of DC electricity. He lived well before the time of Edison, and he's a very interesting character, a very likeable character, and he lived in the time before there were scientists. In fact, he was from northern England, and there was a Reverend Whewald who was, I think, in Cambridge, and who had some problems, and befriended Faraday as a person. So Faraday was the son of a blacksmith. He became a printer's assistant at the age of 7, I believe, and he taught himself to read by setting a printing press, and taught himself science by arranging the printing of science books. And in fact, there were various books designed for popular people to teach their daughters, people to teach girls science, and he learnt from it. And he was a very practical, self-taught person, a strong experimentalist, and he lived in the time before scientists. In fact, people were so impressed with him, they actually invented the word scientist and the theory of science because of him. So he's really important, and he later in life, when the actual mathematical strength of the science wasn't there, he went into education, giving talks, and sat on some key committees which injected science into the public school education. So he's a very central person here. And he's a very practical person, and he really discovered that if you had a little wire and change the flux, the magnetic flux in that little wire, I think I should be able to do this one. If you change the magnetic flux in this group of wire, which is this, oh come on, that's strange. Why is that not working? Nikola Tesla is our third option, and he wasn't an advocate for DC electricity. He had a strong understanding of how you could manipulate AC electricity to overcome, to increase the voltage and reduce the loss in power lines. So he was Serbian. He came to America as an immigrant. He was very badly treated by Edison, who treated him with contempt because he was not, I suppose, an American, and he was a science person, someone who actually did understand things and could be treated badly. Now, his understanding is deeply confused because he believed in magnetic fields, the invention of Faraday, and he believed in fluids and fluxes, and his understanding ultimately wasn't intensely mathematical. I myself can't quite follow what he says, but he did understand that you could create a flux and a voltage, a basic Faraday's law of induction, and so he understood that. And so besides him is an air-coupled transformer, so there's an air core in it, so therefore it can go to very high frequency. At very high frequency you can get very high voltage step-ups and the Faraday effect. I was just going through the internet to the next slide when I came across this quote, and I think it really sums up in a sort of complex way Tesla. And Tesla was indeed not what we call he's more of a scientist than Edison for sure, but he didn't necessarily have command of differential equations, advanced science. And he came up with this saying is that today scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relation to reality. Now, this in fact is actually deeply, deeply true, because we have wandered off and built quantum mechanical devices such as transistors, transformers, also computers, lasers, and they actually don't correspond to what was the reality at the time. So it's a sort of it's a statement, but it's also the insight into what we are. We have actually wandered into a world where it's dominated by these beautiful equations, and that may seem very permanent to us. It's actually a limitation of this thinking. Westinghouse himself was more, I suppose, more educated than Edison for sure, and Faraday, having a formal education, and he himself was an inventor, and so he invented the air brakes for trains. Now this is important, that the train situation, the railways in the United States was a financial bubble, so the trains, lots of money came in, a lot of finance came in with trains, so the invention within the train network introduced him into finance, and it was a more mature industry, so people had to rely on other people's industries, and it's more complex structure. So he brought that structure into the electricity industry and recognised the potential of alternating current. So he was, although people see him as a businessman and a financier, he was also a scientifically literate businessman. So he went into direct competition with Edison to distribute electricity. So there was a short-term conflict between these two people, but that was essentially it. So Westinghouse, very interesting to see him more than just the one sentence. He was a financier. He was actually a scientist trained in financing from the railway boom to actually bring about the next generation, the electricity boom. He had the idea of expansion and finance for another industry in what he was doing. This is an endnote on transistors. I accidentally put one up when I was describing what an AC and DC circuit was, or circuit diagrams, and had a little bit of discussion of what a resistor was. And going through here, there's a couple of points that I really want to make about transistors. So essentially, one always has a circuit diagram with the larger electrode at the top, like this. So that's positive. It's unfortunately the way this is drawn here. Now, the important thing here is that we're going to say that these transistors are placed in this circuit in this way. And you've got 3 electrodes in it. See this little arrow here? This arrow here is basically the direction of current flow, and so in this case it's just going to make it a little bit easier. Oh, come on. Oh. The current is flowing through here. And the current always flows in this direction, so each transistor, this little arrow has to be pointing in the direction, so it's always must be positive to negative. Now, the important thing here is that so the arrow must always be pointing down, but also if the arrow is going towards the base, so in this case the arrow is going towards the base, it's a PNP, positive, negative, positive configuration. You've got 2 configurations, PNP or NPN. Both are pretty much functionally the same, but how you put them in circuits is slightly different. But note that whenever you sit in a circuit, the current must be oriented such that the current is there, and if the arrow is going away from it, you realise that is got a I don't know quite how to describe it. That's if the arrow is going away, it's an NPN. And the way that I remember it, just bear in mind that I'm slightly dyslexic, is that I have an away arrow out of that N in there. The away arrows are put in my head a bit more. So if it goes towards the emitter, it's a sorry, the base. It's stuff. Now, the other important thing to notice is that functionally these devices operate such that if you increase the voltage across here, so the voltage from here to here, so if I have here the voltage and the resistance, what happens is it's got the characteristic that as the voltage increases, the resistance increases, right, for a particular value of current you're putting in here. And so what that means is that transistors are in fact constant current sources, devices which provide constant current, and this is the thing just really poorly explained. And so as you increase the voltage, the resistance increases, and so what you have is this, is that for a V, I've got the I here, for a particular V, like this, you can vary the voltage as much, but the current is the same. But as you fiddle around here, increase a tiny bit more current in here, you create more carriers in here, and it goes like this. So your curve for a transistor is not a single curve as you would have in a resistor. It's a multiple curve thing. But the important thing is that it is a current amplifier. That is, it takes a current in here and it amplifies the current. So this may be, say, 10. This level here may be 100. And that may be 0.1, 0.01, incredibly small current. And so as that small current changes, it's a current amplifier. Of course, the current amplifier can then be put into an old resistor, and you can change it into a voltage increase. You can put resistors in there, and then that will amplify the voltage. But essentially, it's a constant current device. So I thought I'd say those two things because I often have conversations with people teaching it, and they don't know. So let's just summarize again, and we'll just put it yellow. Big one is, let's look at, yellow control. It's these things, these arrows here must always be going in those directions. And if the arrow is going towards the base, it's a PNP. If it's going away from the base, and you sort of get a sense of that, it's an NPN with two configurations. And essentially it is a current amplifier. It's a constant current unit. So the current through a transistor is constant, and it is set by adjusting the feed current, and you feed a tiny current into it and it will specify what current comes out of it. So once you know that, they're very easy and beautiful devices to look at. Thanks for listening. I'm going to finish this small pilot program and get into dealing with a few more questions along the way.